Start with a little bit of an introduction to myself. My name is John Sue, as you can see on my face. And I've always been really excited and interested in learning about how natural processes can get imprinted on landscapes. And I grew up in Turkey partly, which is why my name is a little weird. The C makes a J sound. And this photo here is Erciyes Volcano in Turkey, where my family is from. And in front of it, you'll see the start of Cappadocia, which is a tough layer that got carved into, and people were able to find refuge and homes in this region. And so growing up in Turkey, it's just been a real pleasure learning about the geology. And so with my PhD, I was really excited to study how nature gets imprinted on observational data. I'm going to specifically talk about, let's see. Okay, I'm specifically going to talk about crystals in this talk. And as many of you know, crystals similar to tree rings can preserve information about their surroundings by growing. But unlike tree rings and trees, they're not stationary. They're constantly moving in the magmatic system. And similarly, they can shrink and lose some of that information. So what I'm going to be doing here is providing you a start of a way we can start thinking about the sensitivity of these zonation profiles that we observe within crystals. The two main observations for crystal zonations are how complex the zonations can be, especially for crystals like plagioclase crystals. Here I'm showing two examples of plagioclase crystals on the left and their cross-section. And on the right, I'm showing the anorthite composition variability from the core to the rim of the crystals. The reason why in this publication I picked out these two crystals are because they're identified to be more or less the same in their profile. And even here we can see that there is a large amount of variability that these crystals are showing within their profile. And that gets me to the second point, which is the heterogeneity in the crystal populations. This is a figure that I stole from Mark Jelinek student's thesis, and I think it does a beautiful job of showing how zonations can have a lot of different types, and that a population can have a lot of variability within just one crystal population, and also illustrating a change in anorthite content along it. So the reason why all of this matters and why we're interested in magmatic systems and what information we can get out of crystals. And to do that, what I'm proposing here is to better understand the sensitivity of the zonations. There have been multiple previous modeling efforts that are showing how zonations can be associated with reservoir scale dynamics. And in this example, I'm showing magma mixing. But similarly, the question that I ask here is, can crystal dynamics at the crystalline scale get recorded within the zonations as well? In this example on the right, what I'm illustrating is some of my previous work that's looking at crystals settling through magma. And what you'll notice is that these crystals have this collective behavior as they advect through the domain. I also identify the residual melt in these simulations, which is the melt that's around the crystals, and show how they separate in some areas for some crystals, but then they also stay together for some of the other crystals. And so what I'm asking is, although there is this collective behavior, can the crystals have a heterogeneity within their own population? A little outline for my talk is I'm going to first walk you guys through the methods section, but then I'm going to dive into the crystalline scale process that I specifically identified to do and I start off with the assumption that I'm modeling a magma that is cooling and crystals are forming. And then I'm going to look at how this crystalline scale process might get imprinted on crystals and what that might imply about crystal populations. The big takeaway from my this presentation, in fact, you guys can leave after I say the sentence, is that we need a lot of geochemical and geophysical evidence for a process to happen, or for us to associate observations to a process. And so with that note, I'm going to walk you guys through some of the observational signatures that I think would be indicative of this fluid dynamic process that I'm going to be analyzing in a little bit. All right, so in terms of the methods, I started off with the assumption that there is a magma reservoir with a hot magma injected into a cooler reservoir. I then zoom into this magma injection and look at specifically the cooling interface. With that, I look at I first look at crystals and how they are moving through the melt body. And so it's important for me to resolve the crystals, and not only just resolve it, but to figure out how the crystal is interacting with the melt phase. And so I have a few equations here. The continuity equation, which is at the top, where VL is the velocity of the melt phase. And then the Stokes equation, we're looking at a viscous end member. And so we're working with the Stokes equation where P is pressure, mu, L is the melt viscosity, and VL again is the velocity, and rho L is the density of the melt. And I also track temperature diffusion, and how it travels within the domain. I'm also resolving the crystals, and you'll notice that there is this FC component within the equations that illustrates how the crystals have a force on the melt, but also the melt has a force on the crystals as well. All right, and so this is similar to the research that that I was doing before. The new contribution that I provide for this research is I include a description of the magma properties, namely melt viscosity, density, and crystallinity, and how it changes with temperature. And to do this, I use rhyolite melts and built an algorithm that looks at the number of crystals within a control volume, and that phase change in the real world ultimately changes the melt density and viscosity, and the way that I do that is by coupling it to temperature. I simulate two different magma compositions. I simulate basalt and dacite, and then we'll discuss how those two systems are going to be different. There are, of course, with many models, limitations. So the main ones that I would like to bring your focus to is that I'm only forming these crystals at a constant crystal density and size. And so the crystals are not growing, and they're not partially dissolving in these simulations. And also, as mentioned, I'm not simulating compositional evolution in such that you can have the residual melt evolving and accumulating in a certain area, but rather the compositional evolution is specifically tied to the temperature. Okay, and here I'm mainly going to be tracking temperature, although crystals form and dissolve depending on temperature, pressure, and composition, and I just picked temperature for sake of simplicity. Okay, so now we're going to jump into the fluid dynamics, and I just want to illustrate exactly what this looks like. Okay, so what you'll notice is that crystals start forming at the cooler top boundary. And as the crystals start advecting and settling through the domain, they also form a cluster. And this cluster is able to drag down the cooler temperatures, and with it, setting up a heterogeneity and viscosity and density within the domain, allowing it to have a more rigid part of this instability. And I call this instability a reactive crystal-driven instability. Before moving on to what this means for crystals, let's first look at the fluid dynamics and how it can be different. So I compare specifically the reactive simulation, where I take the same initial crystal distributions, to the non-reactive simulation, and look at the projection of the simulation with time, and try to show you guys the same two different time steps where the clusters are at a similar depth. And what you'll notice is that there is a self-sustaining instability contribution with the reactive instability. Okay, and so looking at our instability, I also simulate a dacitic system where the crystals are forming within a much more viscous melt, and the crystals are hindered, and therefore we actually do not see the simulation coming about. And so then we realize that there's actually this tension between the speed of the crystal settling and also diffusion of temperature. And if we were to look at the same system in a non-reactive simulation, the change in viscosity would end up resulting in the same instability, but at the end also at the same non-dimensional timescale when using the crystal settling velocity to get at the non-dimensional timescale. To describe this process, I come up with a non-dimensional number that I call K, and that is really looking at the speed of crystal settling relative to the speed of the thermal front. And what you'll notice is actually this is very similar to the Rayleigh number, except that I'm using the crystal size A as a length scale here. All right, and although we saw that this instability can readily form in the domain size that we saw for basaltic systems, they might also happen in dacitic systems as well, even though we were not able to resolve it in the given domain size that we were looking at here. And even thinking about this a step further, the reactive crystal-driven convection can arise and feed other flow dynamics and magmatic systems, but I'm not going to say too much more about that. Because we were able to capture this crystalline scale dynamics in the basaltic system, I'm going to stick to that for the rest of the talk. And now what I'm interested in doing is looking at what it means for the crystals themselves. Okay, so here I'm showing two different histograms, one for the basaltic system and one for the dacitic system, to really understand what this crystalline dynamics really means for our simulations. And I'm looking at the crystals and at which temperature that the crystals originally formed in, and what temperature the crystals either terminated or as in dissolved, or at which temperature the simulation terminated and the crystals preserved. If the crystals make it to the end of the simulation, then I call those crystals to be in equilibrium. And if the crystals actually dissolved in the simulation, I am still able to keep track of them, which is one of the benefits of the simulation, and show what the temperature distribution would bend. These two simulations that I'm showing here illustrate that in a dynamic crystalline scale dynamic system, there are actually a lot of crystals that end up dissolving. And of the crystal populations, so that's why you actually see more orange in the left figure instead of the right figure. And that most of the crystals in both simulations show cooling, but some of them in the more dynamic system can also show heating. Okay, so then the next question that we can ask here are, where are the crystals in and out of equilibrium? In order to do that, I break up the simulation into 5 sections and look at the temperature profiles of the crystals with time. And these are crystals that have lasted till the end of the simulation. The blue profiles are indicating an overall cooling. Red means predominant heating, and then gray I indicate as neutral. So this simulation is showing a large-scale process of magma cooling, which is well represented in A, where a lot of the crystals are actually forming. But as you go down through the simulation and look at the most interesting part, in my opinion, which is the tip of the instability, a lot of the crystals actually end up getting dissolved. And so, of course, this has implications of what that could mean for crystals. Okay, to look at longer zonation patterns, what I am doing here is looking at a larger simulation. And the fluid dynamics are, again, I think quite interesting, but I'm going to reserve myself from talking too much about it for the sake of time, and identify different subpopulations within the simulation. The blue crystals are crystals that initially start on the left side of the domain, and the green ones are initially starting on the right side of the domain. And the purple ones are subpopulation of the blue crystals that end up terminating at the bottom of the domain. And so I'm going to pick two crystals for each of the subpopulations and look at their profiles. The green crystals that I randomly picked show that the crystals begin similar to one another in profile, but then they diverge after a certain point. The purple ones have this oscillatory zonation pattern, but then eventually converge to a similar profile. And then the blue crystals have this crisscross process. The main takeaway that I want to show here is that no one crystal is representative of a subpopulation, and the crystals can have very different and dynamic zonations based on given our simulation. And although I'm not simulating a specific volcano, temperature variations within crystal profiles can have implications on compositions that the crystals in natural samples could be preserving as well. And that is really going to determine for how long this instability lasts for. So if we have this instability going on for years, you can imagine that the crystals could be preserving that information. And then finally, how fast the crystals grow will also be able to determine whether or not the crystalline scale dynamics would be resolved. For example, with zircon, this type of behavior might be a little bit more difficult to capture because of their growth rate versus if you were to think about plagioclase crystals, which have a faster growth rate. And so these results are showing that there can be heterogeneity in crystal populations. And so what I'm going to do here is compare this to the two plagioclase crystals that we saw in the beginning. And in the crystals that are in this example, the natural crystals, are in dacitic magma. And so there, the viscosity is much higher in those systems as compared to basaltic. And so they have a greater amount of time the crystals have a greater amount of time to preserve the crystalline scale dynamics, because the variability within the magma can be very slow. And that's going to be determined by the viscosity of the magma. And so if we were to be thinking about a more basaltic system, the distribution that we see here might be much sharper. And similar to what is observed in these crystals, where they have different profiles, similar profiles, and then different profiles, a combination of some of the profiles that we see on the left can potentially result in similar patterns that is captured in these plagioclase crystals. All right, so I'm going to bring back this figure from before to make another point, in that the crystals in our simulations tell a biased story about space and time. Most of the information, as mentioned before, the crystals are predominantly preserving information about panel A, but then E is not necessarily well represented. And so if we were to collect random crystals between C, D, and E, most of the crystals will be very short-lived and also not representative of the entire domain. And so this brings up, this can be relevant when thinking about hot versus cold storage, because in our system, if you were to sample some of these crystals, it would suggest, because of the size of the crystals or how long they've been present, it can underestimate the longevity of the hot magma. Okay, so then the main takeaway from this research is that it highlights the need to have multiple geophysical and geochemical indicators when suggesting a process. And there are other research efforts that are showing similar results in crystalline data. Okay, and so with that information, what I'm going to do is look at some other observational signatures of the reactive crystals-driven convection that I'm studying here. Outside of zonations that we looked at before, there can be other crystalline scale, and in fact larger scale indicators of the reactive crystal-driven convection. The first one I'm going to talk about are glomerocrysts, and again bring up this simulation. As the crystals in the simulation are dragging down the cooler melt, they're also bringing down some of the residual melt and some of the information which they originally formed in. And with that, they're dipping into a hotter magma that has different conditions. And so one hypothesis is that the reactive crystal driven instability could be incubating an environment that is different from the magma that is surrounding it. And a glomerocryst might be able to form in this incubated environment that's again different from what's surrounding it. Another observation in our simulations are transient crystal force chains. Crystal force chains have been suggested and modeled and thought through for crystal-rich systems where stresses can translate through the crystalline network to form as force chains. But Philpotts also suggested that crystal force chains could arise in low crystallinity magmas. And here is one example of how that might actually happen. Within the crystal instability that we are observing here, we see force chains happening at really high crystallinity regions of the domain, although the large crystallinity of the simulation is quite low, in this case, 15%. And then what I'm doing is highlighting here the crystals that are in contact with one another in red or in close proximity to one another. And you can imagine that this has larger scale implications of resistance to deformation, which is what Philpotts actually analyzed in their research. And then the final observational signature of this instability is the depositions of these clusters. So as these instabilities are forming, although I'm not simulating an entire magma reservoir, the domain bottom allows there to be deposition like features in our simulation, where the clusters travel through the domain and then they spread out at the bottom of the domain. And this could be similar to these depositions that have been observed in different geological sites, forming these layered distributions. All right, and so in summary, what I've walked you guys through is that the reactive crystal-driven instabilities can form when thermodynamics are coupled to fluid dynamics. And that has crystalline scale implications in that they can form complex zonation patterns and result in heterogeneity in the crystal population, which is really dependent on the growth rate of the crystals. And I also identify some biases in our crystal populations that could also have implications on natural crystals, and namely that the heterogeneity within the crystalline scale can actually overprint the broader system scale trends. And all of this further highlights the importance of studying multiple observational indicators. In the future, what I would really like to do is I've only just started quantifying the uncertainty within the zonations, and I would love to be able to do more of that, potentially looking at different growth rates. And another idea is to start looking at diffusion profiles instead of only capturing the temperatures in which these crystals are sampling. I also want to highlight that I'm trying to turn this research into an art form, and hopefully I will be able to have that available on my website. So at the end of the month, please go ahead and check that out too. All right, thank you.
Thank you, Jansu. That was great. We have time for discussion and questions, and I see there are a few chat questions here, and I'll probably get started with those while everybody else thinks of other questions. Looks like the first one we have is from Mark Jelinek, and so he's writing about some of the crystal dynamics, and he writes, when you dissolve crystals, what are you actually doing in the simulations? Do resulting buoyancy effects enter? Do these buoyancy effects modulate the gravitational instability you are showing?
Yeah.
Okay.
Yeah, Mark, that's a great question. So I do it in a quite simple way. When the crystals are dissolved, it does not actually change the melt properties of the magma that I am simulating. The magma properties and the melt properties are solely dependent on temperature, which then I use the rhyolite melt simulator to back out what the density and the viscosity of that melt would be.
Thanks. As kind of a similar line in a way, Mattia writes, talking about buoyancy of crystals, is the pressure gradient accounted for in the equation for crystals? So in the equation of motion?
Yeah, 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 yeah. Yeah, absolutely.
Okay. Other questions? Please just raise your hand, or you can, oh, we've got another. This is a question from Ben Andrews. And he writes, it seems like the crystals are in instantaneous equilibrium with the model melt. Real crystals, of course, take time to appear, nucleate and grow, or disappear or dissolve. Can you look at how faster or slower crystal kinetics would affect the processes by adding a lag time to the crystal appearance or disappearance?
Yeah, that is actually something I can do. Um, uh, that is something that I'm hoping to do in the future, incorporate that into the model. It wasn't so readily um, obvious to me how to do it. But I think in terms of a theoretical sense, it would be worthwhile to do, um, and start looking at that. Along the notes of that, the simulator, um, which is available if anyone is interested in using it, would be able to simulate a growth and shrinking too. It's not uh, that difficult to incorporate into the simulator, but because it wasn't so obvious as this initial work has been to incorporate that, I didn't do it.
Great. Mattia had a follow-up. Did you look at the effective crystal size?
Yeah, so the effect of crystal size is just so interesting. It can hinder the instability. So if you have small crystals instead of large crystals, the growth of the instability will take longer, and potentially might even be hindered completely, such that we don't actually resolve the instability, or we don't see the instability.
That was great. We're getting a number of chat questions. This is great. So Alan Lerner is writing, do you have an idea about the scalability of your findings, or how scalable these are for larger magma reservoirs, still spatial sizes?
Yeah. Uh, That that's a very interesting question. And that's not something that I was specifically looking at for this simulation or this research, because that wasn't the driver of my research. But I think that's very important to think about when considering larger simulations of what this could mean. I'm doing a few more simulations to really understand the importance of the size of the domain, and yeah, and I hope to be able to give a uh, more full explanation of the fluid dynamics once I've done that.
Excellent, thanks. Other questions? Well, while people are thinking about it, I actually kind of had a question thinking about some of the thermal implications of the crystals. In that, do you keep track of for example, you have relatively concentrated areas. Does the crystal sweeping around and sedimenting, does that impact the thermal state of the system significantly?
Hmm.
Or are they always in instantaneous thermal equilibrium with the melt?
They're always in equilibrium with the melt around it. And I am now thinking if there is a way. So, yeah, so the thermal diffusion within the crystal in the simulation is said to be the same as the melt that's around it. But if you were to change that, um, I think that would be able to capture some of that variability. Yeah. And so
Sounds
the
good.
way that the crystals actually drag down the cooler temperatures is um, with the melt that's surrounding it as well.
Right, dragging the melt. Okay, yeah. It looks like Ben has a follow-on about the latent heat treatment in the model. We're
Yeah,
asking a lot of technical questions. Hopefully that's okay.
that's okay. Yeah. So that is a simplification that I make, that I do not simulate latent heat, and I imagine that would actually become quite important for the instability, and that it would be worth considering in future simulations.
Other questions out there? Well, I found I found force chains intriguing anyway, but I had a question about the force transmission in the force chains. Are you looking at these like the stresses that crystals impart on each other as well, or are these just sort of transiently swept in due to the fluid dynamics?
So I don't actually look at the forces that the crystals have in this research, only showing that there are these transient moments in which the crystals are next to one another. But one can imagine that if those crystals were to stay in contact for a prolonged period of time in nature, those crystals would be able to grow into one another, and force those transient force chains in my simulation would actually become less transient and more long lasting. And that too has implications in terms of observational data. So, see if I can go backwards. Uh, yeah. So, what Phil Potts is doing in these simulations, which is, or in his observations.
It looks like we're just seeing your probably your screen background. Yeah, maybe.
Okay. Does this work?
Yeah, that's perfect. Yeah.
Okay, cool, cool. Okay, yeah. So what Phil Potts is doing in his experiments is taking a Holyoke basalt sample here and heating it up until there is a certain amount of crystallinity and looking at whether or not there's resistance to deformation. And so you can imagine that these crystals have pre-formed, and they've likely pre-formed, connected to one another, grown into each other. Whereas in my simulations, the crystals are doing almost the opposite. We're starting from the melt phase instead of the solid phase, and we are forming these crystals. Um, and yeah, and so I think it would be interesting to also look at if this transient component were to be longer lasting, and uh, if you had an entire set of crystals that had even more force, how would that translate across the domain?
Right. Yeah, absolutely. Looks like we have actually a few more questions here in the chat. And feel free also, if you want to speak up, go for it. If I'm butchering anybody's question, this is a question from Sam. Um, are these all dry simulations? So in effect, are the volatiles undersaturated? How might this affect your results?
Yeah, that's a really great question. The way that I really started off the journey of this research is being interested in bubbles, and how the bubbles would ultimately alter some of the observational dynamics that we see here. And so stay tuned. That's my next thesis project, of looking at how the bubbles forming within this instability could alter the dynamics that we are observing here, and what that could mean in terms of magma mixing. So I haven't done it yet, but I'm hoping to do it.
Okay, stay tuned. Okay, and then Stefan asks, with the large differences in zonation patterns implied by these simulations, how different do crystal populations have to be in natural samples for them to be clearly identified as resulting from different processes? And would the magnitude of the variability scale with composition, for example, diffusion, viscosity, and so on?
That who asked this question? Sorry,
Stefan. And
Stefan.
hopefully you can see the questions too.
I When I'm sharing my screen, I can't see it.
Okay.
But I think that's a limitation on my
We
end.
can we can definitely go piece by piece. That's easier too.
I think that's such a great question. And that is, yeah, and that is exactly what I would love to be able to think more critically on. And if anyone would like to discuss that with me any further, I would love to chat. Uh, yeah, and that is a difficult question for me because I'm just now starting to think about how sensitive these crystals are, and what can the different growth rates or diffusion profiles tell us. So instead of necessarily looking at 10 versus 50 versus 100, so on, crystals, given a crystal, can we look at multiple different contents to try to figure out a more holistic story? And that's effort that's already being done, like in Kathy Cashman's group and so on.
Absolutely. Yeah, and if I should add that, feel free to, I think everybody has permission to unmute themselves if there's a discussion. That's perfectly fine, in fact, intended. So if there's any follow-up, let us know.
Hi, yeah, I have one more follow-up. You're going to be looking at the side of my face because I have two screens going.
That's fine, yeah.
I was just quickly looking back at the Philpott's paper, and his experiments were running somewhere like over the day to 2-day length scale. Now, I was surprised by the shortness of your simulations. In like about 300 seconds, the thing was turned upside down.
Yeah.
How does that work? Because from just playing with melts in the laboratory, that seems very fast to me.
Yeah, so we're looking at very small domain sizes. And so that's kind of how it's working. And the crystals are relatively large relative to what is actually happening in natural samples. And so this is much more on the theoretical front of research, but ideally you'd be able to set up the parameters well enough to really tackle the problem that you're looking at. And so it's much more on the theoretical front when it comes to that.
Thanks.
Yeah.
Other questions out there? You can chat or you can just raise your hand and we can bring that up. While people may be coming up with the last question here, I do want to remind everybody that if you want to attend the MCS webinars next week, I put at the very top of your chat the link to sign up for those, to register for those. So go ahead, and if you want to do that, just click on that link. Those are webinars, so they're slightly different format. They'll be kind of more webinar format than this kind of a little bit more interactive, but there'll be plenty of time for questions there too. All right, well, I think what we'll probably do, maybe.
I was also going to say, Stefan, for your question, the simulations that I'm showing here are at large depths, whereas, so at high pressures, whereas in Philpott's, they're at, I believe they're at atmospheric pressure. Yeah, and then the other thing to note is that 2D simulations are going to be different from 3D results, and I think that's important to note for these simulations. And so we have to be comparing really apples to apples and oranges to oranges. And so the simulation that the sizes, the speeds, and so on and so forth that you observe here are not going to directly compare to laboratory experiments, unfortunately.
And I have to apologize, I missed Colin's question. Colin had a similar question. And Colin, jump in if you want to put any nuance based on these answers, but I'll read Colin's question. Thinking about the example of layered deposits you mentioned, would sedimented crystals tend to have more or less zonation based on their travel history? Wondering if there are signatures based on trends of zonation in layered crystal deposits. So maybe I'm paraphrasing Colin's question, but do you see a correlation in zonation patterns in layered regions, layered deposits?
Yeah, I haven't personally looked at that. I think that's a really interesting question. I would have to collaborate with someone who has a lot more experience with looking at these crystals, and yeah, to really understand that and find some literature on that. But I don't know.
Any follow-up on that front, Colin?
No, all good. I wasn't too sure if you'd have experience on the deposits front.
Yeah.
just figured I'd ask.
Yeah. Thank you.
No
I
worries.
think it's a great idea.
All right. Well, what I think we'll do now, we're getting towards the end here, is I think we'll thank Jinsu again. But we'll do is if you're cool with it, Jinsu, is we'll just kind of stick around here. People can filter out. Almost always there are a few people that want to discuss things in a smaller group, and so this will be the equivalent of people watching the podium at the end of your talk with questions. So we'll stick around for a few minutes. So if you want to talk for a few more minutes, stay here. But otherwise, please join us next week for the MCS webinars. That's both Tuesday and Thursday next week. Thanks, everybody.
Yeah. Thanks everyone for joining.
Hi, Jansu. Great talk and nice responses to all of our questions. I have to go here in a minute, but we should bounce some more emails back and forth. I finally sent a reply to your AGU email a couple days ago.
Yeah, I saw that. I will definitely get back to it.
Yeah, no sweat. And yeah, this is nice work. So I look forward to seeing more. So.
Thanks, Ben.
Yeah, that was nice, Jansu. I think with a lot of these questions, you can't answer them until you really start scaling the size, the growth rate, and also the intercrystal diffusivity. Because my hunch is I haven't worked on those layered deposits, which look really cool. But my hunch is that a lot of that detail is going to be diffused out because they're accumulating in this very hot system. So the diffusion rates would be high.
Yeah.
And then just one caution about the Ginebra example in those day sites and all the spectacular plage zoning, the crystallization there is probably largely governed by water content and decompression. So there is a thermal signature in there. But then you also are in a system where the plagioclase, I assume, are pretty similar in density to the magma.
Mm-hmm. Yeah.
That's what we think, so that they're not going to be moving around. So it's sort of a challenge because the nice heavy crystals in a low viscosity magma like olivine, it would actually be, the thing to do is, instead of looking at major elements, because iron and magnesium diffuse really quickly, so it just re-equilibrates. But if you thought carefully about where the best system where to look at this, it might be interesting to look at minor and trace elements.
Yeah.
I'm thinking like Makapui lava lake.
Okay.
Kilauea Iki lava lake was quite complicated, and you had all these weird things like, olivine crystals going up because of bubbles. Speaking of bubbles.
Yeah.
But it would be interesting to think about some of the very slow diffusing trace elements that actually might preserve things. It's all about preserving the signature as well as making it, but it's very thought-provoking.
Yeah, absolutely. Thanks. Thank you so much, Kathy. And I think, for a reason why I've been using plagioclase crystals is because they are able to preserve some of the information, it seems like.
Right.
And with these really viscous magmas, I wouldn't be surprised if you had a lot of potentially denser crystals that are settling through, dragging some of the plagioclase with it.
It could be, but the bubbles might be doing more in the opposite direction.
Yeah, absolutely. But so then there might be some dynamics that like crystalline scale dynamics. It doesn't necessarily have to be that this this instability is exactly what's happening, but any form of small scale dynamics is what I'm interested in looking at.
Yeah, well, as you know, the plagioclase populations of intermediate rocks are just all over the map. And in a single small thin section, you get this wide array of crystals with different cores and different zoning profiles. And they're a mess. So we definitely need help on what to do with them.
Yeah. Thank you so much. And I really do appreciate your help throughout, with these conversations. It's been really nice.
Where Kathy's comment started was that these are high temperature systems, which makes diffusion fast. And they also stay hot for a long time because they're so big.
Mhm.
So you have a combination of high temperature and long time.
Mhm.
I have a question about sort of the chemistry that you used. And I was wondering how you actually sort of fed these, fed the system so that it could get the different compositions of the different crystals.
So I don't actually simulate the anorthite content. Oh, but so you're talking about the basalt and the
Mhm.
they say, oh, okay. Those are the two end member cases for the Unzen volcano. And I took the compositions for basalt and dacite there and plugged it into the Rhyolites simulator.
Okay, cool.
Yeah.
Cool, thanks.
Hi, I have a follow-up question to that actually. How far away would you be from, say, calculating anorthite content using this sort of feature that you've developed using melts and the mechanics that you've introduced?
So coupling the content variability within the simulator.
Yes.
Yeah, I haven't done that, but I think it can at least simulate a content and see how that varies and moves around within the domain. And I don't see that being as difficult, but I think once you throw in multiple different contents, it might be a little messier.
Right, because I would imagine it would be much more computationally intensive to track each individual crystal's chemistry. So on that, how many crystals did you allot as a max number for these simulations? Was it it was in the hundreds, I think I gathered?
So I don't cap the number of crystals I can form per se, but it's really on the spacing of the crystals. So these crystals are randomly forming, and there is a packing. What is the highest crystallinity that these control volumes can really reach, and that's going to be around, I believe it's 35%, 35 to 40%.
Okay. Yeah, I mean, it would be really interesting to see that, I guess, with the mechanics that you've introduced. So yeah, again, really cool simulations. It was awesome to see the talk.
Appreciate it.
Well, that was excellent. And I was going to say, we should chat about some of these zircon calculations we're doing too, Jansu. That's sort of in the similar sort of vein as these sort of things where we're looking at basically age populations and zircons tracking crystals. So
Yeah, and I think for those simulations, it makes a lot of sense because zircons have a different time scale of growth, whereas for my simulations, it's much more rapid.
Well, and also zircons, even though they're quite dense, they tend to be very small, which means that they're more likely to be carried or reflect the melt flow rather than just sediment out.
Right.
But I'm glad you're doing bubbles. Several years ago, Allison Rust and I put in a proposal to NERC that wasn't funded. That was, we wanted to examine the role of bubbles on lava lake convection because everyone was just modeling the thermal part, but you have enormous amounts of bubbles coming out. So we did have a master's student play around in the lab with some bubble driven convection, but we became convinced that it was actually really important, especially in the shallow system where bubbles are big and vigorous. So yeah. I'm glad you're going after that.
Thanks. Yeah. Well, we'll see how that goes. I'm hoping to be able to tell a story about magma mixing and how, and also bringing in concepts about enclaves and how bubbles could travel through the interface either effectively without necessarily mixing with the upper layer magma reservoir versus when do they become a proponent of mixing. So yeah.
Well, it's dinner time for me.
So
I'm going to sign out.
We appreciate it.
Thanks, Jansu.
That was great, Jansu. I don't know if there are any last questions out there on things. Okay, well, let's call it a day. Thanks so much, and we'll catch up again soon.
Yeah.
Good seeing everybody.
Thanks. Bye.
Bye. And I would say, Eric, we might as well. Oh, Eric's gone. See you guys.